that we could do with it would be looking at the reactivity of individual molecules. So we've got two nitrogen-containing compounds, pyridine and pyrrole. How would we expect those nitrogen compounds to act? Y is a base. I don't accept big. Because there's a lone pair of electrons on the nitrogen is pretty much it. Nitrogen can't or doesn't stabilize those electrons as well as oxygen, so those electrons are pretty much basic. So now the question becomes is which of these would be the stronger base? What should we be evaluating? Charge, size, electronegativity. All three of those options are dead ends because it's the same. Okay. So then we'd move to resonance. Do we have any resonance options for either of these structures? Okay. And to kind of do an end run on it, usually we'll get people saying, yes, absolutely there's resonance. This can do resonance. That is absolutely valid resonance. That has nothing to do with the base strength. Okay? Our focus for this question is dealing with the lone pairs on the nitrogen. So that's what I want to see. Can those lone pairs be involved in resonance? Both cases, no? The right one, yes. So immediately, what is that going to do to its base strength? It's going to lower it. Okay. And we might consider it lowering a little bit. It turns out it lowers a lot. Why would it lower a lot? Right. It's not so much, and yeah, it puts negative charge on it, but that's not actually going to matter. Right. What happens when it picks up that hydrogen? What is different? Pyrrole in its neutral state versus the conjugate acid. It's actually not anti-aromatic, it's non-aromatic. Pyrrole starts aromatic. What do we know about aromatic structures? They're stable, they don't react. For pyrrole to act as a base, what do we have to do? Lose aromaticity. That is such a disfavored process that pyrrole won't act as a base. Okay? So we can use aromaticity to explain reactivities, okay? Particularly when we're looking at acid and base strength. Okay? It's kind of a secondary topic because in my opinion, we're really just saying resonance. Resonance is all we really needed to do. We didn't have to evaluate this concept of aromaticity to get there. Okay, we're at least acknowledging that resonance. Okay, does that make sense? So we can look at some reactivities and predict reactivities of different bases based off of aromaticity. We could also use it to explain acidities. Okay. What kind of chemistry would you expect for this molecule? Why an elimination?
Because you have a positive charge there.
Does the atom want to be positively charged?
No, it does not.
So what does it want?
It wants electrons.
Electrons. So where is it going to get the electrons from? Okay, so one option is going from the pi bond. The result is now just resonance, so that doesn't really do anything to stabilize that positive.
The base could come and take away the hydrogen.
I did hear, I'm going to come back to that, I did hear suggestion of a leaving group. Yes, we have bromine as a leaving group. If that left, does that help the positive charge? No, if anything, that makes it worse. So this is where looking for those charges comes in handy and not looking for pieces necessarily. Does that make sense? So we don't want to look for leaving groups per se. We want to look for charges. Wherever that charge is most likely to be, then I can evaluate, do I need a leaving group? Do I have a leaving group? Okay? So in this case, I have that positive charge. Bromine is going to be a horrible situation for a leaving group because the remaining structure would be highly, highly unstable. Why would it be highly, highly unstable? Two positive charges next to each other. What do I need to stabilize that positive charge? Electrons. Where are there electrons? Yes, you address the pi bonds. Where else? We could look at the bond to the H. We could take those electrons, or we could take the bromine electrons. Which electrons should we take? Why should we take the electrons from the hydrogen and not from the bromine? When we talked about resonance with oxygen and carbon and carbonyls and all of that, we said the electrons go to the more electronegative element. Which is more electronegative, bromine or carbon? Bromine, which means that blue arrow makes no sense. If anything, those electrons should be going that way, which we established results in an invalid structure, so that doesn't happen. Which means the only place I can get electrons from would be that hydrogen. I'm losing that hydrogen. Okay? That would suggest that this structure would then be acting as an acid. It's donated H plus into solution. How acidic would you predict this structure to be?
It's got charge, pretty acidic.
Okay, pretty acidic. We're neutralizing that charge. Why else might we predict this to be really acidic?
You're going to form an aromatic ring.
The product of the loss of that hydrogen is now an aromatic ring. So we're starting at a very highly charged, high energy intermediate, and if we get rid of that hydrogen, we end up with an exceptionally stable structure. Okay, so that structure is actually quite acidic. Kind of make sense? Okay. This becomes an important intermediate, which we'll see in, I think, 2 slides. Okay. What we now have here is our summary for the rest of the semester. That's it. Okay. Everything is right there. I don't think there's anything that we will talk about that isn't already on this slide. This addresses all the little bits and pieces. It's now just a question of dealing with those bits and pieces and seeing examples. Kind of make sense? Okay. So if you're in that kind of mode where you just need to memorize, this is not a bad slide to print out and just constantly memorize. Okay? So our primary focus is electrophilic aromatic substitution. We talked about it in the lab, so we'll go through it kind of fast here for those that aren't in the lab. Electrophilic means we're looking at something positive. Aromatic means we're looking at, okay, not just a ring, but very likely to be a benzene ring. Before I deal with substitution, would I expect the positive to be associated with the ring? Okay, so it makes sense for me to go through and draw the structure where the positive is on that ring. No, why not? Why not? When you see that ring, what do you see? To be aromatic, what do you have?
It's like extremely acidic. You have electrons.
You have electrons. How would we expect a ring to act? As a nucleophile. What charge are nucleophiles? Negative. Does it make sense to attach the positive to it? No. Okay? So we're looking at a positive coming from somewhere else and a benzene ring. Those two things will react. How do they react? How do they react? It's in red. A substitution reaction. So whatever that electrophile is needs to substitute for something in green. What's in green? Carbons and hydrogens. Which is the most likely thing for that E to substitute for? Carbon or hydrogen? Hydrogen, because
On the outside.
it's on the outside. It's the most accessible atom. Okay? If we look at it the other way, for it to substitute for a carbon, we'd have to break 4 bonds and make 4 bonds to do that full substitution. So it makes the most sense to end with the electrophile attached. Okay? So it did a substitution for H+. We now have our overall reaction. The question would then be our mechanism to set this up. In our mechanism, what do we have? Well, we established what the ring should act as. A nucleophile. It has electrons. It's going to donate electrons to our electrophile. The result, whoops, undo that. Sorry. I'm going to try and, I can't mimic it, never mind. Deal with it. We have our electrophile. We still have the hydrogen attached to the structure, and then we'd have our positive charge. Okay. That positive charge is not stable, so what happens? Resonance. Okay. Generating a new positive charge, which isn't stable, so what happens? Resonance. Okay. So we would do a couple resonance structures. I'll leave you to figure out what the middle one looks like. And if I draw this right, we would be here. What happens? We can remove the electrons from the hydrogen, taking us to our final product. That last step is a nice, easy, favorable step because we're restoring aromaticity, which is very stable. H+ is a more stable structure than whatever that electrophile is. That's what drives this reaction forwards. Okay? Those structures, and actually leave you to figure it out. Ta-da! There it is. Okay? We'll address that in a second. Okay? Those structures in between are known as your sigma structures. Okay? They're all determined based off of resonance. Nearly everything in EAS is based off of resonance. Okay? So if you're comfortable with resonance, EAS should be easy. If you have a hard time with resonance, EAS is going to be a pain in the butt, and you'll probably just need to memorize that previous slide. Okay? So, interesting question came up. Do we need a catalyst? Well, does benzene react? No. Everything you've heard is that benzene doesn't react. That's what we've been preaching for nearly a year now. Okay? Clearly it does. Is it something that's easy to make react? Probably not. So what are we going to need to add? Probably going to add a catalyst. Okay? So those specific conditions to force the electrophile to react with it, okay, are what we're going to evaluate. Okay? So we have two pieces, the nucleophile, the benzene ring, and the electrophile, whatever that secondary piece is. What we're going to start with is what is the electrophile? What are the things that we could attach to it? Okay, we need our electrophile to be very electrophilic, so we want to make it more positive. So if we take a look at those examples, which of those is the most electrophilic? 1, 2, 3, left to right. What do you think? Which one's the most electrophilic? Why? All right, and everybody going, well, that was a stupid answer. That is exactly the answer. Every single time we run a reaction and look for electrophiles and nucleophiles, that's exactly what we're doing. Sometimes they aren't inherently obvious positive charges, right? And we have to dig a little bit. But 2, the middle one, is going to be our most electrophilic. Okay, between 1 and 3. Why 3? When we go through and look at a resonance structure, what do we see? We have a partial positive, or we have a formal positive in the resonance structure on that carbon. That's what makes that structure more electrophilic than our bromine at the beginning. Those of you saying, well, doesn't the bromine steal electrons? Yes, it does once the sigma bond is broken. Is the oxygen stealing electrons from the carbon right out of the gate? Yes, because it's a pi bond and I can draw resonance. Okay? So we're trying to find those hidden charges. Sometimes they're more apparent than others. Kind of make sense?
Couldn't you argue that the nitrogen is also controlled by this resonance structure?
Feel free to draw as many resonance structures as you want. You will have a very hard time showing the nitrogen carrying a neutral charge. You can try it. It's not going to happen. Every single resonance structure for number 2 will have the positive as a nitrogen, or the nitrogen as a positive. There isn't one where it's neutral. Okay? So we might expect 2 to react immediately with the ring, 3 might react a little bit slower, and 1 we may not expect to react at all. Okay? So we might want to speed up the electrophile. Okay? So what I'm trying to do is get that bromine, so let's look at just bromine now, get that bromine to steal those electrons. How could I increase the likelihood that that bromine would steal electrons? Because if it does, what happens to the other bromine? Becomes positive. So what could I put near the red bromine to help it be like, take the electrons away? You could put something near it that would be positively charged, like a hydrogen from a carboxylic acid. Okay? Acetic acid is used as a potential catalyst to help polarize that bond and help us get a more positive bromine. What else could we do? Whoops. We could use a catalyst like iron tribromide, a slightly different catalyst. The acetic acid acts as an acid catalyst, a Bronsted-Lowry acid catalyst. Why? What is acetic acid? A Bronsted-Lowry acid. That's why it's a Bronsted-Lowry acid catalyst. Is iron tribromide a Bronsted-Lowry acid? No. But bromines are all very electronegative. Iron is a metal. What charge does the iron carry? A positive. What can happen? The bromine can coordinate to the iron. That coordination is now not going to be a Bronsted-Lowry definition, but a Lewis acid catalyst. Okay? So depending on which catalyst we use, we get a slightly different name, but it ends in the same result, a positive bromine. Could I polarize 3 further? As a hint, 2 we polarized by having that bromine steal electrons. Where's our electrophile in 3? The carbonyl carbon. So the suggestion was to add a base. What does a base supply? Negative charge. What's that negative charge going to do? It's going to attack our carbonyl. Yeah, that's not so good. But anything that's going to destroy the electrophilicity. How about an acid? What happens if I just add a Bronsted-Lowry acid, H+? Where's that H+ going to go? Oh, it's going to go to the carbonyl, making a positive on that oxygen. Does oxygen want to be positive? So what happens? It steals the electrons, giving us that formal positive on the carbon again. Make sense? Just like with the bromine, we could also add another catalyst. We could also add a Lewis acid catalyst. What is special about aluminum trichloride? It's a Lewis acid catalyst. Why? I'll accept that. And aluminum's kind of borderline. I want a better answer. But all of it was perfectly awesome and fantastic. But I want a better answer. No. The aluminum. Your focus is on the aluminum. What's the better answer with aluminum?
Aluminum has an extra space, just like boron.
Aluminum is happy with only 6 electrons around it, which means what's left over? An empty p orbital. What could we put in that empty p orbital? Electrons from our chlorine. Once those electrons shuttle out, chlorine would carry a positive charge. Does chlorine want to be positive? No, so what does it do? Steals the electrons from there. What do we end up with? A positive carbon. We allowed to form just positive carbons, though? We have to have some reason for that to be stabilized. Why is it stabilized? through resonance, and at least a few people in here should know why this is cool, or why it's a bit silly. Oh, come on. It's a silly ion?
Yeah.
It's a psyllium. It's my favorite ion. This is known as the psyllium ion. Okay? We got a triple bond out to that oxygen, which usually causes most students to freak out and say, absolutely, that's the wrong answer. And it usually is the right answer. Okay? So watch out for that. Be aware of the resonance being able to stabilize in. That's one of the reasons why we can form that reagent. Okay? Can I erase? I just saw a couple people writing. Okay. Okay. Do we want to be concerned about the nitro in between, the NO2 plus? Should we try and make that more positive? Yeah, probably not. Why? It's already positive. We don't need to make it more positive. Okay? So, reagents. Okay, our electrophiles with Lewis acids. We can start with Cl2 and iron tribromide, or trichloride, sorry. Okay? That generates that nasty looking intermediate in between. That center chlorine doesn't want to be positive, so it steals electrons from its partner chlorine, giving us a full formal positive chlorine. Without an octet, that's now wickedly electrophilic and is going to react with our benzene, giving us the Cl positive electrophile. Okay? Does it have to be chlorine? Are there other elements similar to chlorine? Yeah, pretty much all the halides, except fluorine. Don't do fluorine. Okay? We could do bromine, Br2. And instead of iron trichloride, it would be iron tribromide. We'll run the exact same process, get you the same type of electrophile. Okay? R groups. What are R groups? Well, let's skip the R group for the moment. Let's look at the bottom one. What do we have here? The psyllium ion. Okay? Which is dangerous to look at, because when most people look at that, they go, oh, the positive charge, that must be the electrophile. Is the oxygen the electrophile? No, why not? It already has its octet. Okay? When you have the resonance structure drawn out, oxygen steals one of those pi bonds. The carbon carries your full or your formal positive. With a missing octet, that's the electrophilic species. So in each of these cases, we're looking at forming the red atom as our electrophilic species. Where did we get the RC triple bond, or the psyllium ion? Okay, carbonyl wasn't a bad place to start. The acetyl chloride. Why might the acetyl chloride be a neat one to be referencing? It's not like we just spent 2 chapters talking about acid derivatives.
It's the best leaving group?
It's our best leaving group. It's our best electrophile. Okay. To help speed that, again, we can add a catalyst. Our aluminum trichloride works. It does some little magic coordination. Okay. And it will show up nicer and neater underneath the slide here in just a second. But before we do that, how do I get a positive R? What is R? Just a carbon. How do I get a positive carbon? Alkyl lithium. What charge would a lithium be? Be a positive, which means our carbon would be negative, so that's not so good. What could I attach to make that carbon positive? Bromine. There's a decent idea, a decent leaving group. For it to react, though, we must have a formal positive charge sitting out there. Would I expect a formal positive charge? Why not? That would be a zero-ary carbocation. Zero-ary carbocations are not stable. So how can I ensure that that carbocation is stable? I need to be looking for tertiary or secondary to form these. Okay. Secondary can form. How would I know secondary carbocations are allowed to form? SN1 reactions from first semester. We know we're allowed to form them. Okay? To help polarize that bond again, that's where our aluminum trichloride or iron bromides can come in to help polarize that out. Okay? You see the same catalyst for the last one. Interesting, same catalyst for two different reactions. That catalyst might be kind of important and useful. Okay? It might be so important and useful that what happens? It's got a name. Okay? Both those reactions are referred to based off of Friedel-Crafts or Friedel and Crafts. Okay? They're going to get called Friedel-Crafts then something else. Friedel-Crafts up here, what are we adding? R positive, what are we adding? Carbon, yes, awesome answer. That's all we're adding, carbons. What is our name for a carbon? The simplest carbon structure. An alkane. So we're looking at alkylation. Friedel-Crafts alkylations when we're looking at just the R group adding. In the bottom case, are we adding just an alkane? No, we're adding a carbonyl with it. What was that piece referenced as? And it might be easier if we provided another part of that root name. It's the acetylation. Okay, or acylation, if you just run it all together. Kind of make sense? Okay. Positive carbons just chilling on their own. Easy? Hard? Hard. Okay? Positive carbons in an acylation chilling on their own. Easier. Okay, which means that reagent is a lot easier to get a hold of than the top one. Okay? Which becomes relevant when we deal with these. Okay? We'll reference this active part later on. It's actually in the next chapter. Okay? To do the Friedel-Crafts alkylation, you need an active nucleophile. To do the acylation, it doesn't have to be active. Okay, why not? That carbon forms in a high enough concentration that it reacts relatively easily and we don't have to worry about it. Okay? What would you expect? I'll accept a couple answers on this. What would you expect as a product? You just shook your head. Why are you shaking your head at me? Cheaters. What would you expect? Officially, we could hit 3 different answers. Okay. First answer would be no reaction. Why might we say no reaction? It's just a benzene ring. Remember, the Friedel-Crafts alkylation needs to be an active nucleophile. We haven't talked about what an active benzene is, so that makes it a little more challenging, but we could run under no reaction as a possible answer. The other possible answer, we do the reaction. Okay, the aluminum chloride reacts. Of course, I showed the arrows the wrong direction, giving us the electrophilic carbon. We then form the bond out to our electrophilic carbon, and we've got an answer. Okay? Does that make sense?
Where did the red bond come from, you're saying?
It's a purple bond,
The purple bond?
this one here. That purple bond is the attack of the benzene ring to the electrophile. So based off of your face, I'm going to guess you want a little bit more of a mechanism. So we're going to do a little bit of a cheat here. We've now broken that structure. We now have aluminum tetrachloride floating around. Our purple bond is the pi bond now attacking. We then go through our sigma structures and end with that structure. Does that make sense? Okay. That is also conveniently the wrong answer. I can't form a primary carbocation. Okay? That's a primary carbocation. Okay? The aluminum trichloride helps with that and allows it to form a little bit, just enough that what happens? You get a hydride rearrangement, secondary carbocation. Now benzene can react. Sorry for the long, weird-looking bond there. And you get the isopropyl. Okay. So what do you think? Alkylations, are they a good synthetic idea? Okay. When I ran this alkylation, how many products could I potentially gotten? Becomes a mess, right? So are alkylations a good synthesis? Generally not. Any point where you have something that you can't control, like rearrangements, you should probably be careful with. So when you see a Friedel-Crafts alkylation type reagent in a question, more than likely they're fishing for some kind of side reaction messing with the system. Okay? So the alkylations are not as good synthetically because of those limitations. Okay? Kind of makes sense?
Wait, so they said minor, so some product does form?
Some does form, which means you get a split in your products, which again means bad synthesis. Right? So you have to watch out for those carbocation rearrangements. Those can be limited by making sure whatever starting material you're working with doesn't allow for rearrangements. Okay? Hybridization requirements. So if we were going to try and Friedel-Crafts alkylate this, what do you think? Would it work? Why not? This needs to react first to go through, and yes, I drew it horribly. I should have made those bromines. To form our electrophile with a positive charge. Am I allowed to do that? No, which means no electrophile. No electrophile, no reaction. Okay? So when you're running your Friedel-Crafts alkylations, you have to make sure you're looking at an sp3 hybridized atom. Otherwise, it's not going to fly. Okay? You're effectively forming a carbocation out of the gate. Okay? It needs to happen off of an sp3 hybridized starting material. Kind of make sense? Okay. More electrophiles. How do we form this is known as the nitronium ion. Also one of my favorite reactions. As a sort of hint on where this can form from, it's a very similar reaction to the formation of CO2. Anybody know how you make CO2? I was kind of kidding. That was too simple. You're welcome. Carbonic acid. H2CO3 will decompose into CO2 and water. So how could I form NO2? Okay. So there was a suggestion for nitric acid. That's going to be a bit of a problem. Does that match the pattern? I would need two hydrogens. And then yes, that would go through and work. If we drew out the structure for the nitric acid, what's our nitric acid structure look like? Wow, you guys are really good at drawing fast. That's awesome. There's nitric acid. I need a second hydrogen. Where do I place the second hydrogen? On the other oxygen. But what can you tell me about nitric acid? It's a strong acid. So if I tried to, say, run this reaction HNO3 and put another hydrogen on it to make H2NO3, you might call you crazy. It's a nice way of putting it. It's not quite the phrase I was looking at, but yeah, you might call me crazy because nitric acid is a strong acid, and by definition, when I hit nitric acid into water, what does it do? It dissociates into H plus and NO3 minus. And what I'm suggesting you try and do is put another hydrogen on it. Okay? Which would mean I'm making nitric acid act as a base. There's no way we could make an acid act as a base, is there? What if I use a stronger acid? Sulfuric acid is a stronger acid. It will donate the hydrogen to nitric acid, making nitric acid act as the base to form that H2NO3 structure, which will rapidly decompose into our nitronium ion and H2O. Right? That's a fun reaction in my mind because we're taking something that you've learned is a strong acid and made it act as a base. Okay? I'm not the only one that finds that cool. I don't know if the ACS finds that cool this time around or not. Okay? But they have for sure found it a neat reaction in the past. Okay? How could I get SO3 as a positive? So this is another potential electrophile. Start with H2SO3. If we look at that structure, where would I put the extra H? That structure is positively charged. I'd be adding another hydrogen to it, which would make it 2+. That sounds kind of weird. I know we've done some weird stuff. In the previous case, what did I need as a leaving group? Water. So maybe to make that sulfur positive, what do I need? I would need water. There we go. Wouldn't that do it right there? That leaves, and that would give me SO3H, positive charge, right? Fantastic, cool, neat. Why are you shaking your head at me? Because you don't think it's cool and neat? What formula did I just make? What compound is that? That would be H3SO. Try again. 4. Positive. How do I make H3SO4 positive? I take H2SO4 and I add H+. So I take a strong acid and I protonate it by... Yeah, you're good. What would I need to protonate it with? An even stronger acid. What's the stronger acid than sulfuric acid? More sulfuric acid. That's it. So to form H, or the sulfate piece, you just take sulfuric acid and you mix it with it. Okay? Why might that be kind of a dangerous reaction? What does sulfuric acid tend to do to most things? Eat through them, destroy them. Okay? So we'll probably get some loss in that reaction just to sulfuric acid destroying things. Okay? But it works. We could do it.
So how come if you just have like a jar of sulfuric acid, it's not just making a ton of H3SO4?
It is. It's also unmaking it because that structure is not stable. Okay? So it ends up reverting back and forth between it. What we are relying on in the EAS reaction is that the small percentage of that electrophile that's made reacts with the aromatic ring. Once it's reacted with the aromatic ring, it can't reverse. It can't go back to sulfuric acid. Okay? Easily. Easily being the operative word, or at least yet. Okay? I think the last one on, oh, here we go. This one's reversible. So what we do is we take sulfuric acid, we mix it with our aromatic ring structure, and we can put on our SO3H. By it being reversible, what does that mean? I can go backwards. To go backwards, what do I need? I would need water. Okay? I do need an acid catalyst to help reverse this, but I would need to add water. So to go in the forward direction, what can you tell me about the concentration of the sulfuric acid? It has to be high. It has to be concentrated sulfuric acid to go to our sulfate substitution, our EAS. To reverse the reaction, what do I need? I need a dilute sulfuric acid solution. So that could be written as H2SO4 with water. It could be written as DIL H2SO4. For that matter, we can actually write out dilute H2SO4. All of those would now do the reverse reaction. That becomes kind of neat because it is the only EAS reaction we've got that is easily reversible. Okay? Which becomes more important when we move into the next chapter. Okay? What's that? Fuming is concentrated. Yeah. So fuming means it is so concentrated that it is literally off-gassing the substance. Yeah, it's pretty awesome. Okay, so you can do that with nitric acid and sulfuric acid. There was an experiment that I tried once with students that required fuming nitric acid. No accidents happened, but it was a bad idea.
What happened?
The experiment didn't work. I think because we didn't have fuming enough. So, and I didn't want to push that further. Pretty much. Yeah. How can we form a positive charge on that tertiary carbon? You've got one quick answer that you should be able to get me because we just saw it on the previous slides. Good job. We could do a Friedel-Crafts alkylation. It's okay. I don't blame you. We could do a Friedel-Crafts alkylation. That one was already discussed, which means not the answer. How can I get a positive charge on that tertiary carbon? Start with a pi bond. Okay? The pi bond has both of those now stabilized, though. How do I get the positive charge in the middle? What do I need to react it with? Not Mo. I need to react it with an acid. What happens? The first step, because I know you got it on the slides. That's fine. The first step protonates it. Where does the hydrogen go?
Over there.
To the terminal position, because it forms a more stable carbocation that way. That step should be a really easy one, because we talked about that
A million times last semester.
a couple times last semester. I would only argue a couple times last semester, but maybe a million times this semester. That was Unit 1. Okay? Nitration, sulfonation, alkylation. You might see the names also pop up. Okay? The next kind of fun one is your benzylic position. Okay? So we've talked about benzenes. We're now talking about benzylic. Benzylic is not referring to an aromatic ring. It is referring to the position next to an aromatic ring. Okay? That is a benzylic carbon with benzylic hydrogens. That benzylic position is incredibly reactive. Why might it be incredibly reactive? Because if I play around with that by, say, removing electrons and forming a carbocation, that carbocation is now resonance stabilized. So the benzylic chemistry, or there's lots of benzylic chemistry associated at that position. Right? We've seen that with our substitutions. We can get SN1 type reactions. We can also get SN2 type reactions. The reason why we're addressing the benzylic position is not so much because it's a review of SN1 and SN2, it's because of this next interesting reaction. chromic acid was a super strong oxidizing agent. If I take chromic acid and a benzene structure that has a benzylic hydrogen, chromic acid will delete all of the other carbons and leave you with benzoic acid. All, in this case, 3 carbons, don't worry about. They have now disappeared. How does it do it? I don't know. Okay? And where we are in the semester, we don't care. All we care about is that it does it. Okay? What about this one? What would you expect to happen? Does it have a benzylic carbon? Yes. Does it have a benzylic hydrogen? No. So what happens? Draw a product. And for those of you being like, I'm not quite sure what you want me to draw, we could try it, phrase it slightly differently. Draw the correct multiple choice answer.
What's a benzylic hydrogen? Do you look on
A benzylic hydrogen is finding the benzylic carbon, and any hydrogen connected to the benzylic carbon is benzylic. The benzylic carbon is the, oh, I'm on a different slide now. The benzylic carbon is the carbon immediately attached to a ring.
Okay.
So
Those two.
this is a benzylic carbon,
You got 2 hydrogens.
and this is a benzylic carbon. The correct multiple choice answer would be
You'd invert it.
it's the exact same thing. Nothing happens. It's no reaction. I didn't flip it, but yeah, we could have done that. Okay? Make sense? So, another quick test. We take toluene, an alkylbenzene, an alkene benzene. Okay, notice this one's slightly different because we have an ene in there. Okay? An alkynyl benzene and an acyl benzene. Okay? Those last two could be a bit tricky. We react them with potassium permanganate. Ooh, interesting. They switched it up. It's no longer chromic acid. Does it have to be chromic acid? No. What does it need to be? A strong oxidizing agent. What is chromic acid? A strong oxidizing agent. What are the products that you get out of these? Benzoic acid. They all go to the same thing. Okay? The last two become tricky. Why do the last two become tricky? We have that benzylic position, but it doesn't have a hydrogen. Okay? But it's the pi bonds attached to those that are now messing with the system and allowing chromic acid or permanganate to react and do the full oxidation. Okay? Kind of, sort of? Okay. How do we put a nitrogen on the ring? Okay. Have we already talked about a reagent that did put a nitrogen on the ring? Yes, we did. Yeah, we did. Which reagent attaches a nitrogen to that ring? HNO3 with H2SO4 attaches a nitrogen to the ring. What else does it attach? 2 oxygens. Is that structure the same as the product we're asking for?
No.
No. What do we need to do?
Get rid of the oxygens.
Get rid of the oxygens. Get rid of the oxygens by doing what? By adding hydrogens. A process by which we delete oxygens and add hydrogens is reduction. To get the nitrogen on the ring, we have to do the nitration reaction followed by a reduction. Why might we have to do that? Why can't I just add a nitrogen, NH2, directly to the ring? What charge would I expect that nitrogen to be? Negative. Why? Nitrogen's pretty electronegative. Isn't the nitrogen pretty electronegative over here? Why is this one not negative? I'm attaching it to oxygens, and oxygens are more electronegative than the nitrogen. I can't put an NH2 on the ring because the hydrogens are less electronegative than the nitrogen, meaning nitrogen would suck the electrons away, making it negative. I can't do negative to negative. Right? So we'd follow it up with a reduction. There's a variety of reducing agents. The one that's straight up kind of old school to you would be the H2 in palladium or platinum. That'll do the same reduction that we've seen in the past. The new one, called a dissolved metal reduction, we take HCl and iron or some other kind of metal. Okay? Typically I've seen it with tin as well. And both of those will go through and reduce the nitro down to the amine. Okay? Yay! More reagents. Okay? This one's extra fun. What does it appear happened? Substitution. But if we tried to run a standard substitution, we might expect the nitrogen would leave, leaving behind positive charge. Can we do that? No. So what do we have to do? All of this. Okay? And you're saying, oh, right now, you haven't even seen the mechanism. Sort of. Okay. The active species in there is that sodium nitrite, okay, which means we're looking at NO2 plus. This takes me a little bit to do. Nitrogen has 5 electrons, oxygen has 6. There's 2 of them, 12 minus 1 because of the charge. We get a total of 16 electrons. Everybody follow that? That's why I asked if everybody was following that. We should add 1. And we get how many electrons? 18. 5 plus 12 plus 1 is 17. Okay, now what do we do? Nitrogen, oxygen, oxygen. Where do we start placing our electrons? On the oxygens. We'll place so that we get 8 electrons on each of the oxygens. How many electrons do I have placed? 16. 17, 18. There are my electrons. I can go through, erase, draw bonds. Does the nitrogen have its octet? What do I do? Pair of electrons from the oxygen. We have a negative over here. There's our nitrite. Why walk through all that? Lewis structure. The very first thing you start out first semester with. Guess what? On the test. You need to know how to do Lewis structure, and you need to be able to do it relatively quickly. Okay? They will particularly do it with charged structures, not neutral ones. Okay, so there's our nitrite. Anybody see anything that it might react with right away? I agree. HBr is a strong acid. Anybody see anything particularly reactive about it now? Might have to do with the carbonyl, the polar pi bond. That nitrogen is relatively positive, which means
Really, out of all that stuff, that's what we're supposed to have done. You got electrons everywhere, you got age. Come on.
okay,
We're supposed to know that.
process of elimination. We go through and evaluate each of those systems. That's all we've got for reactivity.
Those electrons on that NH2, on that nitrogen, not gonna, I mean, they're gonna, you did all that work, they're gonna pick up electrons,
From another nitrogen.
because he doesn't.
Why would the nitrogen on the aniline share with the nitrogen instead of with that oxygen? So what I believe is getting asked
No, I didn't.
is we have the purple oxygen versus our blue nitrogen up top. Why is the blue nitrogen more likely to react with our red nitrogen than the purple oxygen just quench the reactivity altogether?
No, I never said anything about that oxygen.
Okay, so which part are you asking about then?
Well, the sodium nitrate and the HBr is all happening all together.
Mm-hmm. Along with the aniline. Step one means it's all mixed together.
Okay. So, I just don't understand why we have to go through all of that and then pull those electrons. So you're saying that the electrons on the nitrogen are reacting with the electrons in between the nitrogen and the oxygen?
No. Our blue nitrogen is attacking what?
Our blue nitrogen is attacking that other nitrogen?
It's attacking the other nitrogen. Why would it do that?
So far-fetched. Because the oxygen wants those electrons?
What happens?
The same thing that's been happening all semester?
Yep. What makes this one stand out and look different? There's no carbons reacting. Yet. Okay. We're evaluating each of those charges, and we have to consider at each stage what is the next most likely thing to happen all the way through. What's happening is we're doing this very, very fast. Why are we picking it up and going faster now?
EASreagents time?
Because we've got the end of the semester as a deadline, and have we already talked about this before? Yes.
So hard to see.
It is hard to see. That's part of the process of working through it and getting that practice so that you can pick up the speed with these. And yes, that takes time. I fully admit that does. Okay. What I'm trying to set you up with is the patterns so that you can try and pick these up. You can very well look at this and be like, I have no clue. This can be one of those questions that you decide to skip. Okay. For those of you that have that content, they need to have some way to see where it's going. This is where it's going. This is a more advanced question. Believe it or not, it gets a crap ton worse with this particular reaction. And so the reason why I would argue that we should be okay with this stage of it is we can at least come up with an explanation for this. Because we will see shortly, we won't have an explanation. Okay? We have to evaluate each of those structures. So let's walk through that one more time. What is the most reactive thing? We've got three structures we're working with. What is the most reactive thing in those three structures? Hydrogen. What charge? Positive. What do I need to find? A negative. Where do I find that negative? In the nitrite ion. Why did I draw out the nitrite ion? I'm trying to see its potential reactivity. Because if I see that negative, yeah, sure, that puts a negative on it. What does that do? That generates a neutral structure. Well, clearly something has to happen because we see a product here. So now the question becomes, how does that structure react? What do we see reactive within the nitrous acid? So that bottom structure now, what is the reactive thing within that structure? There's a polar pi bond. Where would the electrons in that polar pi bond go? Why to the oxygens? It's more electronegative, meaning that nitrogen carries a positive charge. What does it need? Electrons. Where do I have electrons? That's the aniline all the way up at the top. Okay? The result of that is that a particularly stable structure? Why not? It's charged, so what do you do?
Kick stuff out that
So the oxygen could come back down. That's one way to resolve that charge. What would it most likely kick out? No, it would probably kick out the nitrogen. Why the nitrogen? It's already charged. So that is a decent technique to go through and evaluate. I want to stabilize the negative, but what does that do in your process? It reversed it. So maybe I shouldn't evaluate the negative first. Maybe I should evaluate the positive. How could I stabilize that positive? The nitrogen could steal electrons from a hydrogen. Right? I don't want the nitrogen getting kicked out. What do I want getting kicked out? I want this getting kicked out, right? That OH is a horrible leaving group. So to help that, I could protonate it. Why could I protonate it? We're under acidic conditions. So now the pi bond can come back down, kick out that oxygen as a leaving group. What have I now formed? Water, yes, I'll accept that. What have I formed? Another polar pi bond. Do I still have potential nucleophiles nearby? Say like a nitrogen with lone pair electrons literally right next door to it. It's going to generate more charge. How do I stabilize that charge? We'll end up cascading through a sequence, and by a sequence it's putting it gently, of acid-base reactions. The end of that acid-base sequence, you will end up with the Benzenediazonium ion. The Benzenediazonium ion is a particularly fun structure. Why might it be a fun structure? It could turn into a lot of things. Why could it possibly turn into a lot of things? What is special about the Benzenediazonium ion? That nitrogen has a positive charge. Does nitrogen want to be positive? So what is it trying to do? Does nitrogen want to be positive? What is it trying to do? Neutralize charge. Where could it get electrons from? Couldn't get them from that carbon bond, making nitrogen gas. Is nitrogen gas really stable? Yeah, it's insanely stable and can easily bubble out of solution. The problem with that, what else do we form? A benzene carbocation. Are carbocations stable? No, so this does not happen on its own. It needs special conditions to force it. It needs special conditions identified by Mr. Sandmeyer with the copper. That copper is what helps facilitate that. Okay? The rest of the reagents, you'll notice you also see copper floating in there in a couple of them. You have really good nucleophiles. Okay? Strong nucleophiles is our iodide. You also get this fluoride being exceptionally negative as well to help out with this whole process. Okay? The Sandmeyer reactions are not commonly tested on, okay? But they are there and you are responsible for them. Okay? If you were wondering about the mechanism, there's 6 steps. Did we get to the Benzenediazonium yet? Nope. So there's more steps. We get 9 mechanistic steps sequencing a whole bunch of acid-base reactions to get to the Benzenediazonium. Ultimately, the point of this is that you now have a structure that you can change the functional groups on and go back to halides if you so desired. Oops, which I think is the next slide. All right. So from the Benzene-diazonium, you can go out to a bunch of different places. How do you get to the Benzene-diazonium? That's the sodium nitrite and acid. Okay. It is a much trickier reaction because of the amount of mechanistic steps behind it. You'll notice that we aren't referencing the mechanistic steps to go from the diazonium out to these final products. Why not?
It's too much.
It's more than we already established was too much. Okay? So there's our summary for EAS. All of our reagents. This puts all of the chemistry on it. What we've talked about, the one thing that's missing here is the Sandmeyer ones. One of the things you have to watch out for is be aware of sneaky chemistry. Acid-base stuff, substituent conversions, okay? Rearrangements, and the Sandmeyer reactions. Those things can be dangerous, so watch out for them. You're responsible for knowing those reagents and knowing that they get to a particular product. So all you really have to do is memorize benzene plus nitric acid makes the benzene or the nitrobenzene. That's what you need. So more so than any other unit, all you need at this stage is to memorize the reagents. The next stage becomes the fun one. Okay. We aren't going to look at a quiz because, again, we're short on time. But what you should be able to go through and do is take a look at each of these reactions and predict what the product would be. Why are these reactions more challenging than what we've just discussed? What's that?
Huh?
Someone mumbled that, I thought. Okay, just a ghost. That's cool. These all already have a substituent on them. These aren't benzenes. Does that substituent, did you guys actually say something?
That's exactly what she said, and she decided not to say it.
Yeah. It's okay.
These all have an extra thing attached to them. This makes it more complicated. Why? Are those hydrogens where we're initiating the substitution the same as each other? No, they're now all different, which means we could get different products coming out of them. When it's just benzene, it matters nothing about which hydrogen I remove because they're all identical. As soon as I drop a substituent on it, they're not all identical anymore. Everything changes. Okay? The thing that's nice about that everything changing is everything changes in a very consistent pattern. What you need to do is take a look at your ring. Our baseline is just hydrogens. This is our zero state. All right, what can you tell me is different going to the top from our baseline?
X with a lone pair.
There's an X with a lone pair. What can you tell me about the bottom one? X with a positive charge. Okay. What does that mean for us? With a lone pair, what can that lone pair do? That can donate electron density into the ring. That then causes electrons to move around the ring. When you go through and draw the resonance, what you will find for that top case is that we can build charge at these positions. Right? What does that mean? If X has lone pairs, those are my nucleophilic sites. What can you tell me about this position? It's not reactive. What happens in the bottom case? It steals electrons from the ring. We'll end up with a very similar drawing, except instead of there being negative charge at those positions, they become positively charged. Remember, in the EAS reaction, what does the ring act as? A nucleophile. In our red structure, what do you think? Is that more or less nucleophilic than just benzene? That becomes more, because what have I done? Put more negative charge in the ring. What happened with the bottom structure? I've put in more charge, so it's not just charge. What charge did I put in? Positive charge, which means the bottom one becomes less active. Remember, this is all EAS. And EAS, what does the ring act as? A nucleophile. When? Always. It's EAS. That's the whole point of it. Right? So the top structure is now an activated ring. The bottom structure is deactivated. With the top structure, which positions are activated? Where's the negative charge located? They're located at positions 2, 4, and 6. Because apparently nobody likes numbers, what did chemists decide to do with those 2, 4, and 6 positions? Name them. Ortho and para. The 6th position is just a copy across of the other ortho. All right? So we could reference that top structure if X has electrons as an activated ring that directs to the 2, 4, 6 positions, or we could call it ortho-para directing, okay, and referencing those locations by a name instead of by a number. Okay? I would make the argument that 2, 4, 6 and ortho-para directing are actually bad things to memorize. Not because the content is wrong, but the order is wrong. What does X have? Electrons. For this negative charge to come out, it has to get by position 1. And what is at position 1? Electrons. What does that do to that negative, that ortho position? Does that make it more active or less active? Less active. Okay? It decreases the ability to react at the ortho position, depending on how large X is. So instead of memorizing your X with electrons being 2, 4, 6 or ortho-para, I would recommend 4, 2, 6 para-ortho. Yes, that drops things out of sequence, and it doesn't sound quite as nice, but it matches the proper substitution pattern. When we move to the purple one, our deactivated ring, would I expect a nucleophilic reaction, or would I expect the ring to react as a nucleophile where there's a positive charge? No. Is there a negative charge in the ring? Negative is a line with a circle around it. No. That's why it's deactivated. Okay, I'm not trying to be that mean. I know what it sounds like. That's why it's deactivated. Where's the only spot that could possibly react then? If those positions are positive, the only spot left over that has any electrons would be the 3 and 5 positions. Okay? So we could refer to that one as 3, 5 directing, and we'll reference that position as meta. Okay? Let's see. So we'll do a couple things just as we kind of end here. There's the summary of those. If you want to look at the the curved arrows to show the resonance, there's all of your resonance for each of those. Okay? That resonance is very, very important. That's what dictates how you get your answers. What I would recommend you go back and do is go back to this quiz slide and classify each of those. What is the X atom that is connected? And note, I'm saying the X atom, and decide where your EAS reaction should happen and predict the product. Okay? With that, we'll